just, I don't know what you. Just heard what you're trying to say.
Seven 30, and today we're going to start the next chapter, chapter 3. It's the language of the computer. It's basically going to cover MIPS and the MIPS essentially. And today, more specifically, I'm going to show you some different classes of architectures that implement size. So the words of the computer's language are the instructions, and basically the vocabulary is going to be the entire instruction set. And here is our topics for this chapter. So we're going to introduce ISA and different ISA classes. That is this lecture. And then the rest of the lectures are going to cover MIPS, how things are stored, what are the different possible instructions with MIPS, and we're going to also cover the different instruction formats. And then we'll end with some other popular ISAs, just a brief overview of those. Okay. So the instruction set architecture, as we know from chapter 1, is the interface between software and hardware. So the way that it's the interface between software and hardware is it's the portion of the machine visible to the programmer and compiler writer, right? And it is this set of instructions that the computer knows how to do. So it's the set of instructions that the computer architect needs to implement. And different architectures have different ISAs. Like Intel is using x86 that they developed. And then this chip, not sure where it's from, but it's implementing the ARM ISA. And just as another note, earlier computers had very simple ISAs. And this is more true now that many modern computers, especially those implementing the RISC architecture of ARM or RISC-V, these other more simple ISAs, we are still using very simple ISAs. But we are also still using very complex ISAs, like x86. So our instruction set architecture, in order to make it very useful, it must pass through many implementations. And this is because, like we talked about before, we want to make sure that it is very portable and compatible with previous compiled hardware. Right, I don't want to release a new ISA every year along with my architecture, because then all of the programs that were written for it need to be recompiled. We need to make a new compiler, right? So we want it to last through many different generations. And we also want it to be able to be used for many different applications. So we don't want an ISA that's solely focused on, say, scientific workloads. And that's all that it's really good for. We want it to be very general purpose so that it can be used for a wide range of applications. And we also want to make sure that it provides convenient functionality to higher levels. So that goes back to the compiler should be fairly good at optimizing, and the high-level programming language should also be convenient for the programmers. But at the same time, we want to make sure that we allow efficient implementation at the lower levels, this being mostly the architecture level. So if we have too complex of instructions, then it's going to be a lot harder for us at the hardware level to optimize and pipeline, things like that. So because the ISA is kind of this interface between software and hardware, and it needs to last a very long time, it's kind of the most critical thing when designing your architecture. So we are using the stored program concept, or this is also the von Neumann architecture. So instructions are bits, and these programs are stored in memory, and they are able to be read or written just like data. So we store programs with the data in the memory of the computer. And then in order to actually execute, we first have to fetch our instruction from memory, put it into the data path of the processor, and the specific place that it goes to is the instruction register, and how we know where we are in our program is with the program counter. So these are two very important registers. And then the bits in the instruction register, which is the instruction that we're trying to execute, kind of determine what the control is of the data path. So it determines what the actual instruction is going to be. And then when we're done with that instruction, we can increment PC to point to the next instruction, and we can execute that next instruction. So here's our execution cycle. First, instruction fetch. Basically, we just need to obtain the instruction from the program storage, right? Then we need to decode the instruction to determine what's the operation, what are the operands, where is the result going. And then once we have their operands, we need to locate them in the register file or wherever they are. Are we loading from memory? Are we storing to memory? Then when we have the operands, we can execute the instruction. So was it an add? Was it subtract? Things like that. And after we execute, we can write back our results. So this is either going to store the resulting computed result into a register, or it could be storing the results back to memory as a store function. So there are three basic ISA types that we're going to discuss today. And the first one is the stack architecture. So a stack architecture is kind of basically like a calculator, right? Your calculator, you have one register, that answer register, right? And if you override it, you don't remember all of the other calculations that you did before. But you can remember your previous ones, so you can do like answer plus 3 if you needed to do multiple different steps. We have accumulator architecture and then general purpose register. So general purpose register is the load store architecture. This is where you can do register to register. So I have two register operands and I'm going to write back to a different, or maybe one of the same registers. I can move data from the register to memory and also memory to the register. And it's also possible to do memory to memory operations. This is not done in MIPS, but you could do this in general purpose register. Right. So stacked machines. So this is the stack model of execution. So this allows us to have very compact instruction encodings. And again, this is used in some calculators. So for a stack architecture, the two operands are always the top two items on the stack. So I'm always going to operate on these top two items and nothing else. So that means in my instruction, I never have to specify what my two operands are. This is why it can be compact instruction encoding. So the operands are removed from the stack and the result is placed back on top of the stack. And you can also have data movement operands. So you can place something from memory to the top of the stack, or you can move something from the top of the stack back to memory. So it's with this push and pop that you're going to put the correct two operands at the top two places of the stack, so that when you do call like add, now you have the two that you wanted to add together. And then if you don't want to use that result immediately in the next operation, you would pop it and put it back into memory. So like if I wanted to do A is B plus C, so we push B, push C. So now B and C are the top two operands. I just say add, right? And then that's going to add the top two operands, which are B and C. And then if I wanted to write that result to memory where the memory location is A, then pop A. So the stack architecture is pretty simple, right? And the main thing for it is this compact instruction encoding, because I don't need to specify any operands. All right. So accumulators is going to be kind of similar to the stack, except now we just have this one register. We have two operands per operation. The first operand is in the accumulator, so the one register, and the second operand is from memory. And the result is going to be stored into the accumulator register, unless it's going to be stored in memory. And this architecture is still used in very low-end machines, so like a microcontroller. And here is an example. So we're going to load B into the accumulator register, add C. So we only need to specify this one operand because the other operand is this accumulator register. So it's going to be B. And then we're going to get C from memory. And then the result from this add is going to be stored into the accumulator register again. You can see with this connection. But if we wanted to move it from the accumulator register back to memory, then we would store A. All right, so those are just two more basic ISA designs. The one that we are going to focus on in this course is general purpose register. So this is going to be based on whether or not memory operands can be used by a typical ALU instruction. That is how we're going to classify it in terms of, are they memory machines? So can I do all operations are just reading and writing from memory? I have no registers. And every instruction contains a full memory address for each operand. And an example of this is a VAX machine. And then here, register memory machines. So some ALU instructions can specify one memory and one register operand. And then we have load store machines. And this load store machine is the class of general purpose register machines that MIPS is. The only instructions that can access memory are load and store. And if you want to operate on anything in memory, you have to first load it into the register files. And then you can operate on the register files. And when you're done with that set of instructions and you have your results, you can then store that result from the register file to memory. So again, MIPS is what we're going to focus on. Okay. So here's the same instruction sequence. So A is B plus C for these different classes. So register memory. Again, first operand is from the register file. Second operand is some memory location. But in load store, both of my operands, I can only operate on things from the register. If I want to operate on something that is stored in memory, I have to first load it from memory into the register files. So here's it. So load R1, so register 1 with B, and then add R1, so the contents of R1, which is the data that was at memory location B, and then add that with data at memory location C. And then if I wanted to store it back to memory, store into memory location A the contents of register R1. Here, I have to load them both, right? Load into register R1 the data at memory location B, load the data at memory location C into register R2. I'm going to add, I need a destination register, and then my two operands are register 1, which contains B, register 2, which contains C. And then if I wanted to store it back to memory, store into memory location A the contents of R1, which was the destination of this app. All right, so why do we have registers in a CPU? Well, it can make our programs faster because registers, which are SRAM, are higher up in the memory hierarchy than main memory, which is DRAM. So it's something on the order of 100 times faster. So we can spend some time loading some of the operands that we need from memory into the register files, then operate on those operands until we're done with all of them, and then go back to memory to store those. The other thing is registers are a lot easier for the compiler to use. There's a finite number of registers, whereas there is still a finite number of memory locations, but it is quite a lot larger than the number of registers, so it's easier for the compiler to optimize. So just to give you reference, MIPS has 32 registers, but it is the ISA that we're working with is a 32 bits ISA. So the largest memory location is 2 to the 32 minus 1. So that's how many memory locations you have. Okay. So 32 is a lot smaller than 2 to the 32 minus 1. We're going to also reduce memory traffic by keeping repeatedly used operands in the CPU. So this is just going back to what I said. Load it into memory, try and keep it, not into memory, but into the register file, keep it there until you're done with it. And then when you're done with it, put it back into memory. This is so that we avoid re-referencing memory. And this also improves code density because we avoid having to specify full memory addresses of an operand. Okay. And the register can be named with fewer bits in the memory location, right? So if we have 32 registers, we only need how many bits to reference any one location?
Just one bit.
32 registers. I need to be able to specify out of all 32 of them, which one am I trying to access? 32 means I have 32 different 32 different locations. So how many bits do I need to specify 32 different combinations? 30.
Oh,
How many locations can I specify with 1 bit?
2.
2. How many can I specify with 2 bits? 4. So keep going.
Minus 1, because then it would be 31. So
Yeah, so 0 through 31, so 2 to the 5, right? So I need 5 bits. Rather than if I have a full memory address location, I need 32 bits. Right? So that is how we have improved code density, because we have less bits for construction. Right. So here's the kind of very similar example. Here's 16 registers, 0 to 15. So we need log base 2 of 16, 4 bits. Right. And we kind of just did this. I forgot that this was a question. But this is the only question, so we can just use the poll as a sentence. So your code is 682. So just answer anything in the poll. And just do it before the end of class. But we're not going to do this question because we just did this, right? The answer here is
5.
Yeah, 5.
What was the number again?
682. 682. So here it is, 32 registers. We have 32 locations, so we need log base 2 of 32, which is so here is our instruction. We have this field to specify what is the operation, right? What is it? Is it add? Is it subtract? Things like that.
You don't use the first and the last for that? I think in the textbook it said.
Oh, it depends.
Oh.
It depends on what this is, what type it is. But we'll cover that in the later lecture. And then you have these different other fields which can be used for other things. Like one thing that you're mentioning is this operation could just tell you that it's an R type. But R type just tells you that the two operands are both registers. And then you need this last field to tell you, is it add, is it subtract? But this operation could also be I type, which is telling you that it's one register and one immediate. And when it's I type, the operation is also baked in here. So it has the combination for, is it add immediate, subtract immediate, things like that. And then this field is the destination register. And here's your two RS, RT, your two operands. So general purpose register machines have been around for quite a long time. So the stack machines, only the top two, this is just the summary, right? So with stack machines, only the top two elements of the stack are directly available to instructions. So you kind of have a lot of instructions that are just kind of moving data around in order to make sure that you're doing the right operation. But in general purpose registers, the CPU storage is organized as a set of registers, which are equally available to instructions. So frequently used operations placed in registers. We are going to be reducing instruction size, reducing memory traffic. And because of these two things, mainly the second one here, reducing memory traffic, we're going to reduce execution time. So stack. The instructions manipulate the top two. You push and pop to transfer data to and from memory. And the example is calculator. The accumulator, the ALU is connected to just one register, which is the accumulator register. And the second is a memory location. And the example is a microcontroller. And then memory. So all of these, again, are general purpose register, right? But there's three different types. So memory. All ALU operations are reading and writing to memory. There's no registers. Register memory. So some ALU instruction can specify one memory location and one register operand. So this example is x86 can do this. And then load store. So only instructions that can access memory are loads and stores. Any actual arithmetic computes, bitwise operation is going to be operating on the register. So MIPS, PowerPC is the ISA from IBM. ARM is another RISC instruction set. And I think we might be ending early here. Yes, because we did not do the poll. That's okay.
There is a second question that's part of the poll. Is that just to answer anything?
Yeah, so just answer anything for the second question. Generally, if there's more questions on the poll than what is on the slides, just answer anything to that. And it just makes it easier for me so I don't have to change the number of questions. And you only have to answer one question in order to get participation. Okay, so you do have reading for Friday, so chapter 3, section 1 through 3. And we can have
Oh.